Hello and welcome to our second photographic process identification webinar funded by the National Endowment for the Humanities. My name is Alice Carver-Cubic and I'm a research scientist here at Image Permanence Institute. This webinar is being recorded and the slides and audio will be available later online. In today's webinar, we will discuss 20th century photographic processes and materials. This is intended to be an overview, and we will focus on the most commonly used processes. We will also focus on how visual characteristics we use for identification are directly tied to materials and technologies used to make photographs. Go ahead and ask questions as they come up, and I will answer them at the end. So you can look to these really great web and print resources to build on the information provided in this webinar. Graphics Atlas is an IPI web resource. Also check out Lingua Franca, a new resource developed by Library and Archives Canada. Sylvie Penchon's book on color photography is also an excellent resource. And of course, anything written by Bertrand Levendrine is going to be great. Remember to sign up for our other webinars. We will discuss 21st century materials and technologies next month. In January and February, we'll present a methodology for identification that includes a step-by-step approach to identification, as well as a controlled vocabulary specific to identifying characteristics of photographs. We've been using this in our workshops, and it's been really successful, so I really recommend signing on for those. So photography is chemistry. An image is formed due to a chemical reaction between certain chemical compounds and light. In the 20th century, silver salts, also known as silver halides, are the most common chemical compounds used. The light sensitivity of chromium salts are also used. So this is sort of what is a photograph. It's an image formed through the use of light-sensitive chemical compounds. There are several photographic processes that were introduced in the 19th century and continued to be used into the 20th century. For more information on these processes, check out the recording from last month's webinar or look at Graphics Atlas. Here is the list of processes we will discuss in this webinar. These were all introduced in the 20th century, or their dates of major use occurred primarily in the 20th century. You'll notice we have fewer processes, but these tend to be more complex. There are a few processes not on this list that were introduced in the 20th century. Processes that had limited use, like bromoil or gum dichromate, will not be discussed here because of time limitations. And we'll talk about digital output processes next month. The types of photographs we see in the 20th century include negatives, positive transparencies, and prints. A negative is a tonally reversed image on a transparent support. That support may be glass or it may be plastic, and the image may be black and white or it might be a color image. A negative is made in camera. Light reflecting off the scene enters the camera through the lens and projects an image of the scene onto light-sensitive material in the camera. The image is projected upside down and backwards. So here we can see a picture of this guy. More light reflects off of light areas like his shirt, exposing the film. Dark areas like his hair absorbs light and reflects very little light, so the film isn't exposed in those areas. This results in an image that is tonally reversed. A positive transparency is a positive image on a transparent support. In the 20th century, these are often made in camera, and like this object illustrated here, a 35mm slide, the image is made in camera is a negative, and then it's chemically reversed to create a positive image. Alternately, positive transparencies can be made by printing a negative onto another piece of sensitized film. These can also be black and white or color. A print is a positive image on an opaque support. In the 20th century, paper, as well as pigmented plastic, are the most common supports for prints. Contact printing was still used in the 20th century, in which the negative is placed in direct contact with light-sensitive paper, so the print is the same size as the negative. However, enlargement became more readily and more easily achieved in the 20th century with the introduction of electric light, as well as chemical improvements or changes to photographic papers, which made them more light-sensitive, or essentially faster. A small negative is placed in an enlarger. The enlarger has an electric light source, a condenser, and lenses. Light shines through the negative and the image is projected onto photographic paper. The print is therefore larger than the negative. So let's talk about the materials. What are the materials that are found in 20th century photographic prints? The image material, so what the image is actually made of, can be metal, it's usually silver, or it can be a colorant like pigment or dye. The binder is usually gelatin. A binder holds the image and suspends it above the support. So the supports that we see primarily are paper and plastic, as well as some glass, as we've already seen. The main use of glass was for gelatin dry plate negatives and positive transparencies. So mainly we're looking at sort of paper and plastic. Paper supports were also often coated with an additional layer. One layer is called the varietal layer, which is the pigment barium sulfate mixed with gelatin, which is then coated onto the paper support. The purpose is to help the binder adhere to the paper. It can also create a smooth surface by covering up the paper fibers. The plastic coating is called resin coating, or sometimes just simply RC, resin coating, RC. It is a pigment, titanium dioxide, which is mixed with the plastic polyethylene. A clear polyethylene plastic layer is also coated on the back of the paper. This serves a similar purpose as the varietal layer, but it also makes the paper waterproof, allowing for faster chemical processing. There's also lots of other additives that were commonly incorporated into the support or into the binder of photographic prints, and we'll discuss those as we talk about the processes. So let's start by talking about silver image formation. It is really important to discuss silver developing out chemistry because it is the basis of nearly all 20th century photographic processes, including color photographic processes. Understanding the way in which the image is formed and knowing what characteristics to look for based on how the image is formed is absolutely key to identification. If you have watched the 19th century webinar, then this is going to be a really nice review. Again, silver developing out chemistry was used in the 19th century to make negatives. In the 20th century, it's used for prints and negatives. The light-sensitive silver halide is exposed to light for a really short amount of time, and a latent image is formed. In the 20th century, short amount of time may actually be fractions of a second. The silver halide is then reduced to silver image particle chemically. Silver developing out requires the formation of light-sensitive compound called a silver halide. This is done by creating a reaction between silver and one of the halogens, chlorine, bromine, or iodine. In this image of the periodic table of elements, you can see the halogens are in the same column, which means that they share some properties. All three of these are used in silver-based photography. In their ionic state, they're called halides, hence a silver halide. Silver halides are naturally only sensitive to blue and ultraviolet light. In the 20th century, scientists figured out how to extend the light sensitivity of silver halides to include green and red light. These are called panchromatic emulsions. This allowed for a fuller range of tonal values in black and white images, and also allowed for color photography to become possible. So how do we get our light-sensitive compound? We start with silver nitrate, which is pure silver dissolved in nitric acid. This is combined with a halide. In this case, we're using sodium chloride. A chemical reaction occurs when you combine the two, and a solid precipitate is formed. This precipitate is the silver halide. Don't be confused by the presence of the nitric acid and the sodium. These are what we call spectators. They're not involved in the reaction. What really matters is the formation of the silver chloride in this case. The silver chloride is the light-sensitive chemical compound. So the silver halide that forms is a crystal, and it has what's described as a lattice structure made up of silver ions and bromide ions. So if you remember back to our high school chemistry or whatever we've taken, atoms are made up of even smaller parts called protons, neutrons, and electrons. The protons and neutrons are the nucleus, and the electrons surround the nucleus, and they're free to move about. Ions are just atoms that have either too many or too few electrons. The silver and bromide are bonded together because the silver has too few electrons, giving it a positive charge, and the bromide has too many electrons, giving it a negative charge. So they kind of hold together like magnets. There's a bit of an attraction there. So the first image shown here is a 3D illustration of the crystal lattice. In this case, you can see the silver and bromide ions bonded together. The bond or attraction is represented by these gray bars. The next image is the same crystal lattice, but as a 2D illustration. The large circles are bromide ions, and the small circles are silver ions. Next is a photomicrograph of actual silver bromide crystals, which are hexagonal in shape. We can't actually see silver and bromide ions, even with super high magnification. We can only see the crystal that they form. The last image is an illustration of the hexagonal shape of the silver bromide crystal. So I'll use these representations of the silver halide crystal in my discussion of silver image formation. So we start with a sensitized photographic material. It's exposed to light either in camera or through a negative, and a latent image is formed. For example, after you expose your print material to light through a negative, there's no visible image. It's what we call the latent image. After exposure to light, the material is placed in a development bath in which the image becomes visible. The material is still light sensitive, so it's then placed in a fixing bath. Fixer is a chemical called sodium thiosulfate. It breaks up all those unexposed silver halides. The unexposed silver halides and fixer chemicals are then removed in this final wash. So let's talk about what's happening during exposure and what the latent image is. The illustration on the left shows the enlargement of a photographic negative onto light-sensitive photographic paper. The following chemical process that I'll describe is the same for photographic film exposed in camera. So as I said before, photography is chemistry. What we are doing when we make a photograph is we are creating a chemical reaction. Most reactions need some kind of energy to push them forward, and light is a form of energy, and our silver halides react when exposed to this form of energy, to light. Again, it's the movement of the electrons that is the basis of the chemical reaction, and this type of reaction that occurs is an oxidation-reduction reaction. If an atom loses an electron, it's oxidized. If it gains an electron, it's reduced. We can remember this by the saying Leo says Gur, lose the electron, oxidize, gain electron, reduce. So in this 2D illustration of the silver bromide crystal, what is happening is that it's showing sort of the formation of the latent image. So let's start here. The squiggly line is our light energy. The light energy bounces an electron off of our bromide ion. Remember, our bromide has too many electrons. The electron bounces out of orbit, away from the bromide, and it gets trapped in this defect here in the crystal. So remember, electrons have a negative charge. And silver ions, they have a positive charge, because remember, they have too few electrons. And so the positively charged silver is attracted to the negatively charged electron. And so the silver actually moves over to where this electron is, and it grabs that electron for itself. The silver ion is reduced to a silver atom. It gains an electron. This process continues and more electrons get trapped and more silver follows until a small cluster of 4 or so silver atoms are formed. This is the beginning of the silver image particle. The seed for an image particle has been planted, but you can't actually see 4 atoms. So we need a lot more atoms to create a visible silver image particle. So the reaction is continued by placing the exposed material into a chemical called developer. The developer is simply an electron source. In the 20th century, we use sort of organic chemicals as the electron source, and this is called chemical development. The electrons from the chemicals in the developer continue to get trapped in this defect, and the atoms continue to form until we have enough to produce a visible image particle. So this is this is another just sort of illustration of what's happening. Here's our light energy. It bounces the electron out of the bromide. It gets trapped here in the defect, and then as the silver attracts over, we get more and more silver atoms until we get this physical, visible piece of silver. When we put our exposed material in the development tray, this is what it looks like. The image begins to form. Pretty cool. So these silver image particles that form are very large filamentary particles. Sort of, you know, it's all relatively large. The size and shape of the image particle dictates the color of the image. And so these large particles produce black image tones. So if all that talk of chemistry stressed you out, here's a calming manatee. You got this. So let's move on. Let's talk about silver gelatin developing out papers. The silver gelatin developing out process was the most common monochromatic photographic process of the 20th century. They were commercially manufactured, and the silver halides were already in the gelatin binder and ready to use. So all you have to do is just buy this paper off the shelf and use it. The process was so popular and so common that silver gelatin developed out prints are sometimes referred to as simply black and white prints. The image is silver. The silver image rests in a gelatin binder. The support is paper, which is usually coated with a baryta layer, or it's a resin-coated paper. So these are cross-sections of actual silver gelatin papers. Here we have our paper support, our baryta layer. This is our gelatin binder with the silver in it. And this is very similar, but instead of the baryta, we have this resin-coated support. So this is a print that we literally chopped up into little bits and imaged it under magnification, high magnification. Because the silver image particles are large, the image tone is black. However, you know, even though these particles are big, they're still way too small to be visible with magnification, or you know, magnification accessible to us. So the image appears continuous in tone. A little definition detour is needed here. The term continuous in tone is used to describe true photographs. This distinguishes a true photograph from photomechanical or digital prints in which a distinctive image pattern is visible with magnification. So here we have true photographs continuous in tone, and here we have two different kinds of photomechanical prints where you can see a very distinctive pattern. So the silver image, going back to silver, was sometimes toned with a sulfide solution, which forms silver sulfide, producing warm brown tones. These are sometimes called sepia-toned prints, as the color brown they produce can be close to the color sepia. Sulfide toning was popular in the early to mid-20th century. Prints were also toned with selenium, which converted the silver to silver selenide, resulting in a purple-red image tone. This was popular in the mid-20th century. So here's our example of our sulfur toning, and here's an example of selenium toning. Sometimes both sulfide and selenium was used together, and this is known as a polysulfide toner. So this example shown here is a set of prints that were all made at the same time and then successively toned in the same toning bath. the selenium slowly depleted, resulting in a stronger sulfide toning in the last prints. So as you can see, toned prints can have a range of image tones from purple red to purple brown to this sort of sepia brown. Toning offers stability to the image as well as changing the image tone. Toned silver gelatin prints usually don't show any sign of image deterioration. Speaking of image deterioration, untoned silver gelatin developed out prints can also look like this due to deterioration. So silver oxidation is sort of one way that it deteriorates. This results in a change of image tone from black to yellow or brown. Fading typically accompanies this change in image tone. The silver image particle loses an electron, becoming colorless ion again. It might find another electron and reduce back to silver image particle, but that particle is much smaller, resulting in a warm brown image color. So again, that size and shape of the silver dictates the color of the image. Smaller particle will give you a warmer color. Or it'll reduce back very close to the surface, resulting in a very, very fine layer of very small silver particles, which we see as this sort of bluish-whitish sheen called silver mirroring. Here is an example of silver mirroring. Or it might just stay in a ionic state, resulting in fading, just sort of loss of visual information. It also might turn into silver sulfide. Silver sulfide happens often if exhausted fixer was used or it was poorly washed during processing, resulting in residual sulfur attacking this oxidized silver ion, forming silver sulfide. Like intentional silver sulfide toning, the image becomes brown. Unlike a toned photograph, an intentionally toned photograph, it will also exhibit fading, and the color of brown tends to be a really unpleasing yellow-brown or even kind of a yellow-green. So the photographic paper manufacturers modified the papers in a myriad of ways to produce a wide variety of aesthetic results. The formation of the silver halide was chemically controlled and modified to result in a range of image tones from a warm black to a cool black. Dyes could be added to the papers, to the baryta layer as well, to produce a range of highlight tones from cream to buff white. So here we have an example of Kodak photographic papers that were produced all at the same time. This was sort of a manufacturer sample set. And what you could see is bright white supports as well as sort of cream white or buff white. So there's sort of a range of highlight colors here. The surfaces were also modified to result in a wide variety of textures and sheens. Some papers have a very thin baryta layer or no baryta layer at all, allowing those paper fibers to protrude, producing a coarser surface and a semi-matte surface sheen. The paper fibers will also be visible under magnification with a thin baryta layer or with no baryta layer. These papers were popular in the very early 20th century. They may closely resemble matte collodion prints in terms of their surface characteristics. However, usually matte collodion will not exhibit any image deterioration because they're toned, while silver gelatin DOP prints that are untoned from the early 20th century often have some form of deterioration, especially if they're mounted to a secondary support. And this example shown here is faded. It used to be a neutral black and white image tone, and now it's sort of this brown color. And it's also, so it also has a shift in image tone as well as just overall fading. And you can see this is the cross section. There's a baryta, but it's very thin, and we get the semi-matte sheen. Particles of silica or starch were sometimes added to the gelatin binder or to the baryta to create a coarse surface. This results in a very matte or a semi-matte surface sheen, depending on how coarse the surface is. These particles are called matting agents, and they will be visible with magnification, giving the surface this sort of pebble-like appearance. So here's our cross-section, a very matte surface sheen, and we get this sort of textured pebble-like appearance. Textures were also applied to the paper support or to the baryta to create a textured surface, which produced sort of a range of surface sheens depending on the texture. If the texture was applied to the support, to the paper support itself, the paper will also have a thin varietal layer. So this is an example of just one of many applied surface textures. So you can see it's this sort of very regular, very interesting texture applied to the surface, and that texture produces a semi-matte surface sheen. There's lots of different textures that were used. So in review, silver gelatin prints can have a range of surface sheens from very matte to very glossy. So this is not what we call a key identifying feature because it can have the range. A thick, smooth varietal layer will produce a glossy sheen, as we see here. A thin varietal layer will give you more of a semi-matte. Matting agents can also produce a very matte surface. So it really runs the gamut. Another addition to the papers are dyes called optical brightening agents. These make the highlights appear brighter. When viewed under ultraviolet light, they fluoresce blue. Manufacturers began adding optical brightening agents in the mid-1950s, and their use increased in the 1960s and were pretty prevalent in the 1970s. Because the silver gelatin developed out process was the most common process of the 20th century, that might help you to identify them because they're just so prevalent. So just kind of keep that in mind. While they can be a variety of image tones and they have a variety of surface characteristics, keep in mind that was the most common process of the 20th century. So let's move on to color photography. Because silver halides were made sensitive to the full spectrum of visible light in 1906, color photography was made possible. All color photography begins with silver gelatin developing out process. So like this painting by Georges Seurat, color photography is an illusion of sorts. The image is composed of additive or subtractive color elements, which the eye blends to produce a full color image. Let's break this down and explain it a little bit. We'll start with additive color. The first color process was an additive color system. Additive color is the mixing together of the primary colors of light, red, green, and blue. When evenly mixed, white light is produced. So this first color photographic process using additive colors is called the screen plate process. Autochrome was the most popular screen plate product that sort of used this idea of this process. So an autochrome is a piece of glass coated with a tacky varnish onto which dyed semi-transparent potato starch grains are dusted, creating a random red, green, and blue screen. A silver halide gelatin emulsion is then coated on top. The plate is placed in the camera backwards so that the glass side is facing the lens, and light passes through the red, green, and blue screen before striking the silver halides and exposing them. The starch grains act as filters. The red grains allow red light to pass through and block green and blue light. Similarly, blue grains only allow blue light through, and the green grains only allow green light through. This gives selective red, green, and blue light records of the scene photographed. So here's our cross-section. Here's what it looks like with magnification. The image is then viewed with transmitted light through the red, green, and blue filter. In processing, it's actually a reverse process to produce a positive image. So of course, when we expose it, we get a negative. Then we do this sort of reversal processing, which gives us a positive transparency. We view the positive silver gelatin transparency through this red, green, and blue filter, and it produces a full color image. Our eye can't see these individual grains, and so we sort of get this illusion of full color. Screen plates are easily identified because they're positive transparencies on glass or plastic support, and with magnification, you'll see the screen, which will always have additive color elements. Autochrome, which is shown here, has a random pattern of color dots, as do Agfa color plates. Other products have checkered pattern, some have squares, some have lines. Each of these products uses different materials to produce the screen, and because they're all made up of different materials, they each deteriorate differently. So it's really important to correctly identify what kind of screen plate you have. Check out Sylvie Penishon's book for a fairly complete description of the different screen plates that were used. And I'm using the term product because the idea of the screen plate, it's really sort of a theory that was introduced by a guy named Louis Ducos-Ducourant. And so the screen plate process is just this idea, and each manufacturer sort of produced them differently. So they're all different in terms of their materials. All other color photographic processes are subtractive color systems. The three primary subtractive colors, cyan, magenta, and yellow, are used. These systems are based on light absorption or the subtraction of light. Each color selectively absorbs one primary additive color while allowing the other colors to be seen. Black is achieved when three subtractive colors are superimposed. Subtractive color photography is separated further into two systems. The first is color assembly, which includes the Carborough and dye imbibition processes. First, I want to describe how color assembly works in general, and then we'll talk specifics. So like our screen plates, color assembly begins by creating a red, green, and blue record of the scene being photographed. 3 negatives are made, each through a red, green, or blue filter, and these are called separation negatives. These negatives are then used to print a cyan, magenta, or yellow image. The 3 color images are physically superimposed to produce a full color image. So in our example, here's the scene being photographed. We have an orange, a lemon, a red apple, and this green plate, red candle. Here are the 3 separation negatives. Notice the images are tonally reversed, so they're negatives, and notice each negative is black and white, but each has different tonal values that correspond to the values of red, green, and blue in the scene. So the red apple and the red candle are darkest in the red record, here. The separations are used to print their complementary cyan, magenta, yellow image. The blue record prints yellow, the green record prints magenta, and the red record prints cyan. So these are the complements. The 3 prints are superimposed to produce a full color image. We print the yellow, we print the magenta, we print the cyan, and we get our full color image. Let's watch that again. Yellow, superimpose the magenta, superimpose the cyan, full color image. So we'll begin by talking about the Carborough process. Carborough is based on the light sensitivity of chromium salts, specifically a chromium compound called dichromate. When dichromate is mixed with an organic polymer like gelatin, the gelatin hardens when it's exposed to light. This is the basis of the carbon process, which we discussed in last month's webinar. The gelatin, the sensitized gelatin, will also harden when it comes into contact with silver. In the Carborough process, our 3 separation negatives are used to make 3 silver gelatin developed out prints. These prints were often referred to as silver bromide prints because silver bromide was the light-sensitive silver halide used. So the name Carborough is a mashup of carbon and bromide. These 3 carbon tissues are pigmented, one with cyan, one with magenta, and one with yellow. They're then squeegeed into contact with silver gelatin prints. The gelatin in the tissues hardens where silver is present, and the unhardened areas that correspond to the highlights remain soluble and are washed away. The 3 prints, these 3 pigmented gelatin tissues, are then layered on top of one another, producing a full color image, just like we saw in the previous slide. So here's a cross-section of a Carbro print. So our materials are, the image is pigment, it's suspended in a gelatin binder, which is coated onto a paper support. These prints also often have a baryta layer, and sometimes they had matting agents. This process could be used to make large monochromatic prints, just as a carbon process could be used to make small color prints. It's usually not possible to tell whether or not the print is carbon or Carbro because the final materials are exactly the same, pigment and gelatin on paper. Carbro tend to be larger than 8 by 10, and they also tend to be full color. This process was commonly used to make prints for advertising. So this is the source material for your 3-color magazine print. So some of our key identifying features include this differential gloss. Because of the way in which the image is formed through the selective hardening of gelatin, the gelatin is thickest in the shadows. So this produces differential gloss, where the shadows are glossier than the highlights, which we can see here. With magnification, you'll see 2 more key identifying features. Assembly prints like Carbro have misregistration, seen as this color fringing where shadow meets highlight. It's not possible to perfectly align 3 prints. Therefore, we get this sort of fringing, this misregistration. Also, because the image material is pigment, pigment particles will be visible throughout the image viewed with magnification. So the image will appear continuous in tone, but you'll have this even dispersal of pigment particles throughout. Same as our carbon process. The next assembly process is dye imbibition. This process uses the remarkable ability of gelatin to absorb and desorb liquid dye. So we start with our 3 separation negatives, and these were used to make printing matrices. These matrices consist of gelatin sensitized with the dichromate on a plastic support, a clear plastic support. The gelatin hardened where it was exposed to light, and the unexposed areas of gelatin are washed away, producing a clear, positive image as this sort of low relief of gelatin. The clear gelatin matrices were then dyed with cyan, magenta, or yellow dye. So here are our 3 matrices. These are 3 matrices. They're on clear plastic supports. Where it's darkest, the dye absorbed, or the gelatin rather, absorbed more dye. So this is our shadows. And then the 3 dye images are transferred from the matrices onto a gelatin-coated receiving paper by squeegeeing the matrix in contact with the paper, each one in succession. So we put down our cyan, our magenta, our yellow. We transfer that dye one at a time onto the receiving paper, building up the image, and this is our full color positive print. So what are the papers? The receiving papers are baryta papers. So the material consists of a paper support coated with a baryta layer and gelatin, and the dye image is absorbed into the gelatin binder. So this is our cross-section. Kodak perfected the dye imbibition process with the introduction of Eastman wash-off relief, which was then replaced by dye transfer. So we often hear this process referred to under its proprietary name of dye transfer. Unless you can data print, there's really no way to know which product exactly was used. There were 3 different dye transfer receiving papers with 3 different surface characteristics. So there's sort of a couple sort of semi-matte surfaces, and there's a glossy surface, different textures. However, all dye imbibition prints share a few common key identifying characteristics. They all have misregistration because of this inability to perfectly align the images during printing. This is still, again, visible with magnification where highlight meets a shadow. It's also visible in untrimmed prints along the edges of the printed image in the border here. And then here in our magnification, it's sort of visible here. Also under magnification, even really high magnification, the image is completely diffuse, completely continuous in tone. It's actually sort of difficult to focus on the image. You feel like there's something wrong with your eyes, like your eyes are going blurry or something, because the image is so diffuse. So our other class of subtractive color photographic processes are integral tripack, in which the red, green, and blue separations are superimposed onto a single support. The cyan, magenta, and yellow dye is also in the corresponding red, green, and blue sensitive layers. The first process we'll talk about is chromogenic. This consists of a support coated with superimposed red, green, and blue light-sensitive silver halide layers. So silver halides in gelatin. These layers also include these colorless compounds called dye couplers, which will eventually form a subtractive color dye. So the chromogenic process is the most popular color process of the 20th century. It begins by exposing the material to light, either in camera or through a negative, depending whether you're making a print or a negative or a positive transparency. The latent silver image is formed through exposure to light, and the silver image is made visible through development. There's our silver image. Remember, silver image formation is an oxidation-reduction reaction. The silver gains an electron, is reduced, and it's the developer that's losing an electron, and so the developer is oxidized. These invisible dye couplers react with oxidized developer to form colorless dye clouds around the silver image particles. So there are our dye clouds. Finally, the silver is chemically removed, leaving with just dye and gelatin. So again, the chromogenic process was used to make negatives, prints, as well as positive transparencies. Therefore, they might come on plastic or paper supports. I should say that the silver gelatin developed out process was also used, again, to make negatives and positive transparencies. Back to chromogenic. Our paper supports can be either Baryta supports or resin-coated papers. The Baryta papers tended to have a thick Baryta layer and a glossy surface. The resin-coated supports began to be introduced in the 1960s. By the 1970s, all chromogenic materials had resin-coated supports. And the resin-coated papers actually did have some applied surface textures, which altered the surface characteristics. So we can have a few different sort of surface sheens, from glossy to kind of a semi-matte or sheen with our chromogenic prints. And of course, the image consists of dye and a gelatin binder. Chromogenic prints often, but not always, have a stamp on the back or are printed on the back of the paper with the manufacturer's name. So a back print or back stamp is a key identifying feature. Look at the back. If there isn't anything on the back, and also to kind of self-check, look at it with low magnification and the image will appear continuous in tone. If you look at it with higher magnification of about 50x, those dye clouds will be visible, and they look like tiny random pinprick-like spots of color. So here's sort of 50x magnification image, and you can see these little pinpricks of color. You can see the dye clouds. Chromogenic prints, all chromogenic materials actually, are susceptible to image deterioration. The highlights yellow and the dyes fade. The dyes fade overall, but at different rates, resulting in a shift in color balance. Dyes fade in the light, but they also fade in the dark. They're just inherently unstable. Light fading results in this overall cyan cast, while dark fading results in overall magenta cast, which is what you're seeing here. And that's because the different dyes fade at different rates, depending if it's in the light or the dark. This highlight yellowing is due to unreacted color couplers that are still present in the materials. These colorless couplers go yellow over time. The dye stability and the coupler stability was improved over time. So, example, Prints made in the 1970s and before often look like this. Prints made sort of the 1980s and on look a little bit better. The color is a little bit more present, if you will. However, chromogenic materials will eventually all sort of exhibit dye fading as well as coupler staining. The next process to talk about is silver dye bleach materials. These are most commonly known by the proprietary names of sebachrome or ilfochrome. So what we have is we have three superimposed light-sensitive silver halide layers, which also contain our fully formed and visible cyan, magenta, and yellow dyes. Exposure and subsequent development produce the silver image. So there's our silver image. The print was then placed in a bleach bath. This chemistry is really complex, so I'm going to kind of give you the cliff notes. During the bleach stage, there's a bleach catalyst that transfers back and forth between the silver image particle and the surrounding dye molecule, which bleaches the image or the dye image until all the dye surrounding the silver particle is removed. It sort of becomes invisible, creating these sort of halos or voids around the silver image particle. So there's our catalyst, and it's basically rendering this dye invisible where our image particles are present. And then the silver is chemically removed, leaving us with dye and gelatin. This bleach bath was pretty harsh and way too acidic for paper. It would sort of destroy the paper support. So silver dye bleach prints are on a plastic support or on a resin-coated paper support. If it's a positive transparency, we'll have a clear plastic support. If it's a print, it's an opaque plastic support or a resin-coated paper. And again, that image is dye and gelatin. There are a few key identifying features that distinguish silver dye bleach from chromogenic. The three gelatin layers have cyan, magenta, and yellow dye fully formed, so unexposed areas like the borders have all three dyes present, producing black, so we have black borders. With high magnification of 50x or higher, we'll see this image grain. Because the image is formed by removing dye around the silver, we see these voids called bleach halos. With practice, these will become easily distinguishable from dye clouds in the chromogenic process. Our final process is diffusion transfer. I'm not going to go too far into image formation of this process because of time constraints. These prints are most commonly called by their proprietary name of Polaroid, although other companies had used this process. There are silver-based black and white prints as well as dye-based color prints. They're pretty easily identified by a back print, which often says Polaroid or gives a date of manufacture as a number code. The image material, when exposed in a camera, whether it's silver or dye, it diffuses over from the negative onto a receiving paper. And then the two are the negative and the print are peeled apart. So as a result, these prints have remnants of adhesive on the border. Under magnification, the image is also pretty diffuse. Internal dye diffusion transfer prints, like for example the Polaroid SX70, as well as the Kodak and Fuji equivalents, are also pretty easily identifiable as they have this white plastic frame. They also have a back print. So that is pretty much it. Thank you so much for listening. Thank you to the National Endowment for the Humanities for funding this webinar. A lot of this information is based on research done for Graphics Atlas, which was funded by the Andrew W. Mellon Foundation. Our next webinar is November 8th, same bat time, where we'll discuss 21st century digital output processes. I'm now happy to answer some questions. At the end, when you close out, please give us feedback. There'll be a short survey that pops up. We really appreciate feedback that you give us. We'll use this to report back to the NEH. We'll also use this to sort of improve for next time. So I will do my best to answer your questions. So the first question I have here is, are sulfide/polysulfide tone prints considered safe to store with other black and white photographic prints, or is the risk of off-gassing going to lead to cause damage of other prints? You can totally store these with other prints. There's no off-gassing. When you when you tone a silver print with sulfide, it's sulfur. It stinks like rotten eggs, and pretty gross. But once it's toned, you actually have a very, very stable silver sulfide image particle. This is super stable. There's no off-gassing. They're totally fine. No problems there. So my next question is, what can conservators do for untoned photographs? I'm assuming you mean in terms of image stability. If a silver photograph is untoned and it's faded, there's nothing you can do to physically bring back that image. Um, the silver image particles, they go from your sort of solid silver image particle back to their ionic state, and then they move about. They move all over the place. They move up, they move down, they move sideways. When they move up, you get silver mirroring if they reduce back to silver image particle. But you also get fading, and there's just really nothing you can do. I think I'm not a conservator, but I think most conservators, the most they do is sort of stabilize. If the gelatin binder is coming up, you can sort of stabilize that. But in terms of bringing back the image, there's nothing you can really do. Okay, the next question is, what are the main deterioration forms of silver dye bleach images? Good question. So silver dye bleach, so unlike chromogenic, which the dyes are inherently unstable and fade, silver dye bleach are pretty stable. The dyes are a class of dyes called azo dyes, and they're really, really stable. They don't fade readily. If you put them on permanent display for like 30 years, they do fade. We do have some that have faded because they were on permanent display for 30 years. The silver dye bleach support, before 1980, it's a cellulose acetate support, and so it is susceptible to deterioration, the same kind of deterioration that cellulose acetate film support is sort of subjective to. After 1980, it's a polyester support. Polyester is super stable. The main form of deterioration that I see in silver dye bleach is actually chipping of the gelatin at the borders. So you can actually see cyan, magenta, yellow layers because of loss of gelatin binder on the borders and the edges. What are the distinguishing features between silver gelatin DOP made in a home darkroom or artist studio versus a commercially made print? There are no key identifying features in terms of the materials. You or I could buy the same photographic print paper as a commercial studio. Primarily, it's going to be subject matter, maybe. Um, I don't know. I don't know if that there's a really good answer. Um, if you're using a home darkroom, it's the same darkroom, the same materials, the same equipment as a commercial photographer. If you're taking your film and you're having prints made by a sort of commercial photo finisher, commercial photo printer, um, like when I was a kid, I'd take my film to Walgreens and I'd come back an hour later and have prints. There's certain sort of sizes and formats that those come in. They're smaller, and that's true even in the sort of early to mid 20th century, sort of 1920s, 1930s. So you can look at format, you can look at subject matter. In terms of the materials, there's not going to be a huge difference. I don't know, that's super helpful. Okay, the next question is, was silver dye bleach mostly used for printing enlargements from positive color slides, or are they made from negatives? That's a really great question. I didn't cover that. Silver dye bleach is a positive to positive process. So actually, the print material is actually exposed through a positive transparency. And it's because of this sort of selective bleaching, selective removing of dyes around the silver image particle. So the silver image, if you were to imagine, the silver image is technically a negative, but you're actually making it a positive by sort of selectively removing the dye around the silver image rather than forming dye. So it is actually a positive to positive process. It's kind of an oddball in terms of how it's exposed. So the next question is, does Polaroid need to be stored in the dark? I would say store all of your photographs in the dark. All photographs are susceptible to deterioration from light. Light is a form of energy. Light will make your photograph, light will break your photograph. So yeah, store them in the dark, totally. Store all of your photographs in the dark. So the next question is cold storage, frozen storage appropriate for all process types. Cold storage will, how do I say this? All of these different photographic processes deteriorate differently. And so for some processes, we highly recommend frozen storage, so freeze it. That includes chromogenic. Because those dyes fade in the dark as well as in the light, it's basically just chemical kinetics. A chemical reaction will speed up with heat, another form of energy that sort of pushes a chemical reaction forward. And so what's happening when our dyes fade is it's a chemical reaction that's happening in there. And so by freezing it, we're just significantly slowing down the chemical reaction. That's really important with chromogenic materials. With other color materials, they don't fade in the dark, so you don't necessarily have to freeze them. So if you have frozen storage, cold storage, that's why identification of color materials really becomes important. Is cold storage is usually limited in terms of how much you can put in there. It's sort of, you only have so much room. You definitely want to prioritize putting a chromogenic material in there as well as any of your cellulose acetate or cellulose nitrate film. Frozen storage won't harm any of your other photographic processes. It's just not necessary. I will say that you shouldn't put internal dye diffusion transfer in there. Polaroid SX70, the ones with the white border, don't freeze those. And actually, freezing them will harm them. So I hope that's a sufficient answer there. Whoa, sorry. Questions are coming and I'm missing it. Can you scroll that down, Lauren? Thanks. What, do you know what processes the new Polaroid cameras use? Diffusion transfer. So diffusion transfer is the black and white. Dye diffusion transfer is the color peel apart. Internal dye diffusion transfer is the internal one. As far as I know, it's still the same process. Let's see. How would you suggest members of the public store the chromogenic prints at home? Oh, oh, wow, that's a tough question. Here's the thing. If you just take your prints and you chuck them in the freezer, your freezer doesn't have humidity control, and you're going to get condensation, and you're going to get sort of too much water in there. If you look at the National Park Service has resources called the Conserve-O-grams, and there is a Conserve-O-gram on how to store photographs in a freezer that doesn't have humidity control. So basically your regular old freezer that you have in your house. And basically you make a double vapor-proof package so you don't get condensation on the inside. However, that is excessive for most people. I think for most of us, our chromogenic prints are just, if we don't have a chest freezer that we can store them in, you just keep them in your house, at the most stable temperature and humidity as you can. Like mine are not in the attic or in the basement. Mine are in a closet they're in my where I keep my sheets, So this is the best most of us can do outside of an institution. Okay, is there a cheat sheet or reference that exists to find out the process used based on the negative brand? For example, trying to identify color process by knowing negatives are Kodak safety negatives. I'm not sure if I can say by brand. IPI, we have another resource called filmcare.org. Go to filmcare.org. It is the sort of graphics atlas equivalent for film. That is 30 plus years of research that has gone into making this resource. It's excellent. Go to filmcare.org for all of your film questions. Let's see. I'll do this one. Okay, what was the change that expanded the sensitivity of silver emulsions for orthochromatic to panchromatic? Okay, so I kind of glossed over this. Silver halides are only naturally sensitive to blue and ultraviolet light. I'm gonna lose the date. The late 19th century, they were extended to include blue and green light. These are called orthochromatic emulsions. So if it's sensitive to just blue and just green, this is orthochromatic. In 1906, they kind of made that next leap forward and figured out how to make them sensitive to red, green, and blue light. These are panchromatic emulsions. So that's the difference. And the way it was done was just adding a really specific dye actually to the gelatin. It kind of surrounds the silver halide and extends its sensitivity in some way. That's advanced chemistry, so there you go. So it's 3 o'clock. That's my last question I can take. If I didn't get to your question, um, I do know where to find you. We have your email addresses, so I'll go ahead and email you the answer. And if there are other questions that you have, feel free to give us an email. You can find me directly if you go to the feedback button on graphicsatlas.org. The feedback, you can email me through there. Okay, thanks a lot, and I hope to see you all next month. Fill out the survey.